So here we're going to look at a real-world application with a rational function. So part of this application we're going to look at, it is using a formula that distance is equal to rate times time. And in fact, it's using a form of this that is solved for time. So if we divided both sides by rate, time is equal to distance divided by rate. So I'll come back to that, but it's something that it's already been used. We don't have to apply it, but just so that you can recognize it in case you've done those problems recently. So we have a river that flows at 6 miles per hour. A boat traveled with the current from town A to town B, which are 210 miles apart. Then the boat turned around, traveled against the current to reach town C, which is 130 miles away from town B. The amount of time it took between the two is the same. During this whole trip, the boat was driving at a constant still water speed. So this constant still water speed means the speed the boat is going without any effect of the river flow, without the idea of going with the current versus against the current. So we're letting x be this constant still water speed of the boat, so without the effect of the current, and then t of x is the amount of time in hours for this trip. So it's modeled by this relationship. So what I wanted to point out in terms of this time equals distance over rate, because this t of x is calculating the total time. So this first piece is the idea of going from town A to town B, where you're traveling with the current. So the distance is in the numerator, as we said it would be, and then the rate, so x is the rate of the boat. Since we're going with the current, it's kind of pushing us along. It's helping us go faster. So it's like if our boat was going 30 miles per hour, if we're traveling with the current, then it's 36 miles per hour. So this relationship is describing from town A to town B. This relationship here is town B to town C, where we have the distance of 130 miles. And then since we're going against the current, it's kind of dragging our rate down. It's making us go slower. So if we were going 30 miles per hour, this would force us to go 24 miles per hour. So I just wanted to show you that so you can understand where these formulas are coming from, but it's all given to you so you don't need to form it yourself. So find and interpret t of 25. So t of 25, we're plugging in 25 for x. So we're taking 210 over 25 plus 6 plus 130 over 25 minus 6. And then we could just use a calculator to help us out. Let's get a rounded answer of 13.6163. And let's figure out our units. So this 25 is a value for x, and that's our speed of the boat in still water. So that would be miles per hour. And this value here is this total amount of time, which would be in minutes. Sorry, need to make sure what is hours. Okay, it's a much longer trip. So there we go, hours. So what we're saying is if the constant still water speed of the boat is 25 miles per hour. The boat is 25 miles per hour. The total trip time is about, let's say, 13.6 hours. All right, so that's plugging in a value into our function and then evaluating. Let's do the same thing, but solving. So we're saying the total time, so this is the total time for the trip, in hours, and we want to find the speed that we would need. So if we knew we only had 10 hours to complete this, what speed does the boat need to be going? So 10 equals 210 over x plus 6 plus 130 over x minus 6. So we're solving a rational equation here. So I need to find my LCD, which would be this x plus 6 times x minus 6. So we want to multiply every single term by x plus 6 times x minus 6. So on the left-hand side of the equation, we'll have 10 times those values equals 210 over x plus 6, multiplying with both of those values, plus 130 over x minus 6, multiplying with both of those values. All right, so on the left-hand side of the equation, I'm going to go ahead and FOIL out here. This is our going to be our difference of squares. So we're going to have 10 times, and then we'll have x squared, and then the negative 6x plus positive 6x will cancel each other out, but then we'll have positive 6 times negative 6, which is negative 36. On the right-hand side here, those x plus 6 values will cancel out, so we'll have 210 times x and 210 times the negative 6 in there, so negative 1260. And then over here, the x minus 6 will cancel, so we'll have 130 times x plus 130 times 6, which is 780. Then I'm going to distribute 10. So we'll have 10x squared minus 360 equals, and then combining like terms with each other. So 210 plus 130, so that'll be a 340x. Negative 1260 plus 780 will be a negative 480. And this turned into something that's quadratic, since I can see my x squared term there, so I need to move everything to one side of the equation and have 0 on the other side. So I'm going to subtract 340x from both sides, and I'm going to add 480 to both sides. So we'll have 10x squared minus 340x, and then negative 360 plus 480, which will be a positive 120, equals 0. Now, solving a quadratic, we could try to factor at this point. However, I'm going to see I have this nice common factor of 10 happening right now, so I'm just going to divide absolutely everything by 10 on both sides of the equation. So then we'll have x squared minus 34x plus 12, and that is much easier numbers to work with. Now, this isn't factorable, so we're going to use our quadratic formula. So we have a is 1, b is negative 34, c is 12. So we're going to have x equals negative plus or minus squared minus 4ac all over 2a. We're going to plug in a, b, and c. And then we'll solve. So x is going to be equal to positive 34 plus or minus. I'm just going to simplify everything under the square root there. Since this is a word problem, we don't need to worry about an exact answer because we're just going to estimate. So 11 over 1108 over 2. And then we'll just use the calculator to get the two solutions out. So if we add them together, it should be a 33.64. If we subtract them, we actually get a positive number, and it should be a positive 0.3567. However, in terms of making our answer, we're saying we're traveling 10 hours. So these are the speeds of the boat. Miles per hour, miles per hour. To travel at almost a third of a mile per hour is pretty much impossible. Also, in terms of making a 10-hour trip, if you're going that slow, that's not a reasonable solution. So that doesn't work. But this 33.64 miles per hour makes sense, especially after what we found in our last example of 25 miles per hour takes about 14 hours. So decreasing that time a bit means a slightly faster speed. So those relate well to each other.